Lesson 5, graphical analysis, acceleration. So, first off, we got to learn about something called instantaneous velocity. From what we've done in lesson 3, remember we were learning about switching from a position time graph to a velocity time graph. We know that the slope of a position time graph is the velocity. We learned those things. Now, what we're going to do is we're going to do something called acceleration. So, instantaneous velocity, though, first off, screen's not working. Okay, I fixed it. So instantaneous velocity, though, is going to just be the velocity at any given moment. So we talked about this in lesson 1, I think, lesson 2 maybe. It's the velocity that a police officer with a radar gun would catch. If you were speeding up toward a police officer, he's going to read a specific instant speed, right? Right when he shines the radar gun at you. So if you looked at something like this, a position time graph, having a curve that indicates something is accelerating, you can kind of see that the position is going up and up and up, right? And as time goes on, it's going up and up and up even faster, which makes sense, right? It means you're really accelerating. You're picking up speed, people say. So if I want to find the instantaneous velocity, though, let's say at what point do we pick here? Point 10 seconds. So that point right there is what we want to find. How fast was that person going right at that moment? Well, we said that the slope of a position time graph was speed, but I don't have a slope here, right? It's a curved line. Like what what sense can I make of that? Well, what we do is we make a slope. So right where that point was, we just make a straight line. This line is called a tangent line. It's gonna be tangent to that curve. You've maybe seen that before in math. There's lines that are tangent to circles. So this one, if you're drawing your tangent line, you pretty much want to just have equal space between there and there as there and there. And that's going to give you a line that's pretty close to tangent to that curve. It's probably going to be off a little bit, but it's good enough for for a lot of instances. So in this case, we just draw that line. We just make it touch that point, and we do our tangent line. And then just like we did in lesson 3, you just figure out the slopes. So we have a rise of 11 meters there. We have a run of 8.4 seconds. So if you go rise over run or distance over time, we get 1.3 meters per second. That's that instantaneous velocity at that point. So you could do that anywhere along this curve. You could do the same thing and find it over here. We'd have our curve would probably, or our line would look probably more something like this, though. Probably better than that. But yeah, just did it quick. All right, so moving on. So here's a situation where you got something that is accelerating, right? So it says the following data was collected when a ball rolled up an inclined plane. So we got an inclined plane here. We got a ball. It rolls up, stops, and then rolls back down again. So that's our situation. It says make a position time, velocity time, acceleration time graphs. Our position time is going to be pretty straightforward. You just really need to plot the points and then just make a line of best fit or curve of best fit to fit your data. This can be a little bit tough sometimes trying to make this actually like one smooth sweeping curve. What you wouldn't want to have is something like, like that or something with a bunch of crooked lines going through there. You want it to be one smooth sweeping curve. We like smooth curves in physics. Okay, so that's our displacement time graph, just to plot that. Velocity time graph. Well, velocity time graph, we need to figure out the velocity at a few points, the instantaneous velocity at a few points. So if we look at this point first, we can do what we did in the last example. This line should be probably touching that curve a bit better than it is. But if you do that, I have the calculation for that one right here. You end up getting 4.2 meters per second. If we look at this top point, and we don't need all the points actually. To make the simplest one you can do is just to use 3 points, and that's what we're going to do here. We're just going to use that point, and that point. You could also do it there though, and we'd have more data points for our velocity time graph. But for this one, we're just going to say, okay, the middle point here. You can see that the slope there is going to be equal to 0, right? It has no slope. It's totally flat. So V3, we're going to call it, is equal to 0 meters per second. And then this one is going to be negative 4.2 meters per second at that point right there, right? And we get the negative because it's dropping 7.6 meters. So remember that. People seem to forget the negative on that. So now we have our data right here. This is the data I found from above. The velocity at 1 second was 4.2, 0 at 3, and negative 4.2 at 5. And now we just need to plot those on a velocity time graph. So if we do that, we end up with a point there, there, and there. And you can see it's a straight line. So a straight line on a velocity time graph it indicates that you have a constant acceleration. That's going to be important. You need to be able to see these graphs like a velocity time graph and know what it means if you have a straight line. Know what it means if you have a horizontal line. We'll go through that a bit more in the end though, but that's just kind of the thing we just learned right now, that straight lines mean it has a constant acceleration. And now that we have a straight line, remember earlier I was saying that we like straight lines in physics because we can figure out what the slope is. If you figure out what the rise over the run is for this, you end up with a change in velocity over time, right? That's velocity on this side, and it's time on this side, and it's a change in velocity on this side. Well, a change in velocity over time, that's acceleration. So if we figure out the slope of our line now, then that is our acceleration. So we can see that acceleration is equal to, down here, acceleration is equal to change in velocity over change in time. So if you do that, just find your slope. It's going to be negative 10 over 4.6. We figured out that our acceleration here is going to be negative 2.2 meters per second squared. And those are our units for acceleration. And you can see if you look at our units here, that's what you would get, because you've got meters over seconds and then over seconds again. This could also be written as meters over seconds times seconds, or meters, that should say m, over seconds squared. So that's where that unit comes from. Okay, so now acceleration versus time. We're going to plot one more graph. This one's easy though. We only have one number, right? We figured out that the acceleration of this thing is negative 2.2 meters per second squared. That's the only thing we need to plot here. So if you make an acceleration versus time graph, we got time going along the bottom. The time for all three of these, by the way, is the exact same. So you can see that, well, the other one's on the other page, but they all go up to 8. So time's going to be the same for everyone. Acceleration, I wanted it to go into the negatives because that's where my number was. So it's just at negative 2.2, and it's just going to be a straight line the entire time. The acceleration of this thing was the exact same the entire time. And that's important to note, because if we go back to our original graph, a lot of people would say that this thing rolling up the ramp and then rolling back down again, they'd be like, well, it decelerated up and then it accelerated down, or that type of thing. That's a pretty big misconception that most people have. This thing had a negative acceleration, which means that its acceleration was pointed down the ramp the entire time. What happened is that we pushed this thing up the ramp, right? It started slowing down, and then it started speeding up in this direction. You can kind of think about acceleration as being a force. It's pretty much is a force. We'll talk about this more later, but so if its acceleration is kind of the thing. If you can think about, there's something pushing this ball the entire time. As soon as I let it go, this ball was going up just because of its own momentum. It was going up the ramp. But then something was pushing it down the ramp the entire time. That's something pushing it down the ramp. That was the acceleration that's pushing it down the ramp. The same type of thing as if I jump up into the air. Most people would say, well, I accelerated upward for like a bit, and then they get all confused by that. Really, the whole time as soon as I left the ground, I was accelerating downward at 9.81 meters per second squared the entire time. We'll talk more about this in a later lesson, but just know that we're only going to be dealing with constant acceleration in this course. All right. So I'm going to end that video there just to keep the topics kind of separated. And I'll see you guys in the next video.